In part 4 of the Introduction to Standardized Echography, we will discuss the instrument parameters that determine the spike height in A-scan and, once standardized, enable tissue differentiation. We said this before, the most important contribution of A-scan, of standardized A-scan that is, to tissue diagnosis is the fact that the spike height indicates the reflectivity of the examined tissue. But the spike height also depends on the probe and on several instrument parameters and settings. Unless they are optimized and standardized, the spike height means nothing. At first, we will discuss the ultrasonic probe that sends out the sound beam. The standardized A-scan probe emits an effective frequency of 8 MHz. It has a flat transducer with a 5 mm diameter. This combination of 8 MHz effective frequency and a 5 mm diameter of the transducer guarantee the sending out of a parallel beam. At high tissue sensitivity, the beam is wide, here seen in a Schlierenfeld picture. At medium sensitivity, the beam is narrower, and at low measuring sensitivity, the beam is very narrow. A parallel sound beam is a must for quantitative echography. Otherwise, the distance of a reflecting echo source would have to be calculated in evaluating the intensity of the echo signal. With a parallel beam, that is not necessary. It is also a prerequisite for recognition of sound beam perpendicularity. When we use a focus beam, we are never sure that we are really perpendicular on a surface, particularly when it comes to B-scan displays. And a parallel sound beam is a must for measuring cross diameters, thicknesses of the optic nerve and the extraocular muscles. Only a parallel beam will be refracted enough in the orbital apex to reach the surfaces of the structures perpendicularly, and perpendicular exposure is needed for precise measurements. Before we go into the discussion of further instrument parameters that influence the spike height, we should clarify first the term decibels and what they are being used for in standardized echography. A decibel, dB, is a logarithmic unit used to express the ratio of two values of a physical quantity. In standardized A-scan, any chosen setting of the instrument sensitivity is set against tissue sensitivity T, which serves as standard reference. This means that a decibel value for a setting of the instrument gain or a setting of the amplification of a signal becomes meaningful only when it is set in ratio to tissue sensitivity T. For instance, a gain setting of T plus decibels or T minus decibels. The decibel units confer a number of advantages, such as the ability to conveniently represent very large or small numbers, and the ability to carry out multiplication of ratios by simple addition and subtraction. On the left we see decibels from 0 to 80 plus. On the right side the amplitude ratio for the amplification. It's easy to see that at low numbers we can understand that, for instance, a little bit more than 3 times amplification means plus 10 decibels, or 10 times amplification means plus 20 decibels. But when it comes to 100 times, 1000 and even 10,000 times, it's difficult for us to understand, to imagine, and to calculate with these numbers. It's easier to use the decibels as plus 40, 60, and 80. There is one number that we should remember. A plus 6 decibel means an amplification to double the amount. Similarly, the decrease in amplification is shown as minus decibels, easy to understand. On the right side we see the decrease in amplification, and again with small numbers it's understandable, but when it comes to the greater amounts of lowering the amplification, these numbers are beyond our understanding and beyond any practical use in standardized echography. Here again, remember one thing: minus 6 decibels is always half of the amplification. And now the next instrument parameter that influences the spike height and needs to be standardized and optimized, it's the receiver. The receiver gets its signals, electrical signals, from the probe that has converted the echo signals into electrical signals. And the main function of the receiver is amplification, so that the signals can be strong enough to influence the display on the screen. In B-scan we use a broadband receiver. That means that a broadband of frequencies from 4 to 12 megahertz are amplified and attenuated equally. Why do we use this? Because it gives us a much better lateral resolution that is needed in B-scan. But the broadband amplification also introduces more noise, and that limits our amplification possibilities. In contrast to B-scan, the A-scan, the standardized A-scan, uses a narrowband amplifier. One frequency that is 8 MHz is maximally amplified, and already at 6 MHz and 10 to 11 MHz we get only half the amplification, and that gets even lower at higher and lower frequencies. That gives us the advantage in A-scan that we can use a much higher amplification without disturbing noise. Plus 20 dB advantage over the B-scan, and that allows us to examine the posterior orbit right back into the orbital apex. There's another advantage of the narrowband amplifier. It is sensitive for frequency shifts, which the broadband amplifier is not. And so it helps to measure absorption and display the angle kappa, which is important in orbital differential diagnosis. Now we come to a very important parameter, the amplifier characteristics that take place in the amplification during the signal processing and make the major difference between B-scan and A-scan, standardized A-scan that is. It's more difficult to understand, and therefore we'll explain it step by step, slowly. The amplifier characteristics determine the way and amount how the spike height reacts in millimeter to an increase or decrease of the echo intensity or the instrument gain in decibel. Let's first look at the linear amplifier, which is often used in B-scan. As we are dealing with a logarithmic scale here, showing the amplification from 0 up to 80 decibels, the linear amplifier is not represented by a linear straight line, but by this curve. Vertically we see the height of the spikes in millimeters as the result from the amplification in decibels. Overall, only 13 decibels can be displayed in differences simultaneously on the screen of the linear amplifier with one gain setting. In other words, the acoustic field is 13 decibels, and that is insufficient. On the other hand, when we look at the decibels needed to increase spike height from 10 mm we need less than 3 decibels to achieve that. And that is an excellent acoustic sensitivity. When we compare these amplifier characteristics with the functions of the human eye, we learn to understand the impact these characteristics have on echography, on the differentiation of tissues, on the acoustic evaluation. Here we have the linear amplifier. When we project it on this visual field, we can see that it has an excellent acoustic acuity going right here to the macula, but the field is insufficient. It's like an acoustic hemianopsia. How about the logarithmic amplifier? The characteristic line is straight because of the logarithmic scale we use. Overall, the acoustic field is much more than we need actually. It's over 70 decibels. All these different intensities can be simultaneously be shown on the screen with one gain setting. As a matter of fact, in echography we would use only a third or less of the screen height during the examination because it's too much acoustic field. On the other hand, when we look at the sensitivity, raising a 10 mm to a 20 mm spike height requires more than 13 decibels, and that is a sensitivity that is insufficient. With the functions of the human eye, the functions of the logarithmic amplifiers are seen here. Yes, no problem with the field, but there is a central scotoma, an acoustic central scotoma. The sensitivity is not good enough. Standardized echography utilizes an S-shaped amplifier curve for the A-scan display. It is a compromise between the linear and the logarithmic amplifier, combining the advantages of those two and avoiding their disadvantages. For instance, the lower to medium high spikes, they react very quickly like the linear amplifier to changes in the amplification. The acoustic acuity is excellent. On the other hand, the upper ends and low ends of the curve slow down the changes of spike height, adding the needed acoustic field that the linear amplifier doesn't provide, and the logarithmic amplifier gives too much of it. Compared now with the functions of the human eye, we see here the results. A good, sufficient acoustic field combined with an excellent acoustic acuity. Let's look now at the echographic importance of the S-shaped amplifier characteristic curve in comparison to the logarithmic and linear amplifiers. These echograms were obtained in the early 1970s from a cavernous hemangioma of the orbit, from a lymphoma of the orbit, and from normal orbital tissues, all at tissue sensitivity. You can see that the weakest signals are still visible at this sensitivity setting, and the highest signals are still not overloaded, still can be evaluated in regards to the height. You also see a difference in angle kappa, almost no angle kappa here, a clear-cut angle kappa, medium size, and a large angle kappa here. So quite a difference between those echograms that assure our ability to differentiate them. When we look at the logarithmic amplifier, in contrast, these echograms look very similar to each other. And the linear amplifier is very confusing because we had to use different sensitivity settings in order to display signals without being overloaded or under the threshold. And finally, an important other issue, the setting of the tissue sensitivity that we have mentioned. The gain setting, very important if we want to evaluate the spike height as a function of the reflectivity of the tissues. Setting tissue sensitivity T of the standardized A-scan instrument means an absolute standardized setting. It is a required prerequisite for all quantitative evaluations and consequently for reliable tissue differentiation. Experiments with different reflectors such as steel or plexiglass surfaces in oil were undertaken in the 1960s by different authors. They all failed since tissues do not reflect but scatter the ultrasound, and there's a huge difference between reflection and scattering. Beginning in the late 60s, we used at the eye department of the University of Vienna citrated blood as a successful tissue model in serving to determine tissue sensitivity or to set an instrument at tissue sensitivity. It was examined this way that the citrated blood was poured into a glass container and the probe was placed from above into the citrated blood. This was the first widely used standardized A-scan instrument that we developed with Kretz technique in those years. And when you look at these echograms from the blood sample, however, blood samples of different cell counts, 10,000 cells per cubic millimeter, 500,000 cells, 1 million, 3 million, 5, 7, 9, 11 million cells per cubic millimeter. How can we get those different cell counts? By centrifuging the citrated blood and then mixing it with a corresponding amounts of sodium citrate, which prevents the citrated blood from thrombosing and keeps it fluid. And you can see that at low cell count or at very high cell count, low or no amount of sodium citrate, almost all sodium citrate, the reflectivity is low. It increases with the cell count and then decreases. We used for the tissue model successfully a cell density of 3.6 million erythrocytes per cubic millimeter. Of course, it was time consuming to exactly produce these tissue models, and they would last only a few days in a refrigerator before we had to go through the whole process again to obtain a tissue model. And without tissue model, we cannot set any instrument at tissue sensitivity. Therefore, it was a great advance when Peter Thiel, who succeeded me as director of the echography service in Vienna in the early 70s, produced this solid tissue model in an ingenious way, permanent way to determine tissue sensitivity. And every standardized instrument since then is delivered together with such a tissue model, which is needed not only in the beginning of examinations with an instrument and a particular probe, but also over time to check the tissue sensitivity, which may weaken when the probe weakens. It is determined for each instrument and probe combination. How is that done? We see here the echogram of the tissue model by Thiel at medium spike height. So the instrument was set at a gain that these spikes had medium height, and we recognize this, that the triangle, echo-free triangle above and the echo-free triangle below are of equal size. And that is then tissue sensitivity for this particular instrument probe combination. A T minus would be when the triangle above is larger than the triangle below, and a T plus when the triangle above is smaller than the triangle below. This is a list of completely standardized instruments that are on the market since the year 2000. The most complete and advanced is the Aviso S for standardized A scan and for B scan by Quantel Medical, available since 2010. It is a portable and all digital instrument. All the documentation is available through a PC. It uses an 8 MHz standardized A-scan probe and 10 up to 50 MHz B-scan probes. Automatic software programs of this unit include quantitative echography 1 and 2, the A1 and the A4 for the diagnosis of detached retina and its differentiation from dense vitreous membranes. For absorption documentation, the angle kappa, an orbital profile for the evaluation and graduation of Graves orbitopathy, and most important, the Cine loop that has changed standardized A-scan and made it so the Cine loop changed particularly the A-scan technique and made it much simpler, easier and faster. All these completely standardized instruments allow for automatic and precise settings of tissue sensitivity using TIL's tissue model.